So we are dealing with problem number 2.6 in this series, and the problem number 2.6 in this series is stating a vertical cylinder closed from both ends is equipped with an easily moving piston dividing the volume into two parts, each containing 1 mole of air. In equilibrium at T0 equals 300 Kelvin, the volume of the upper part is 4 times greater than that of the lower part. At what temperature will the ratio of these volumes be equal to 3? So let us approach this problem by first of all drawing a diagrammatic situation of the problem which is given to us. So now one thing to understand in this problem is that the two vertical cylinders are there. So the piston is going to exert certain force in the downward direction. So this is the situation which is given to us, that each of the chamber is containing 1 mole of the gas. Each of the partitioned chamber is containing 1 mole of the gas. Initially it is having 300 Kelvin temperature. So we are considering that at equilibrium the pressure over here is P1 and over here it is P2, and the volume ratio is already given to us as V and 4. So V0 and 4 V0 in this case. And in the second scenario, the question is asking us to what final temperature should it be heated that the ratio becomes V and 3V. So over here we have taken V dash and 3V dash. Again it is containing 1 mole of gas on the either side and the pressure being P1 dash and P2 dash. So what is connecting the two cases is the mass of piston and its cross-sectional area. So if we draw FBD of piston in each of the case, then we will be able to obtain a situation. And the next thing which is connecting is the total volume of the cylinder, which is same, that is total volume V here is also equal to total volume V here. So if we write an expression for V0, so we can write 4V0 plus V0 is equal to total volume V. So over here we can write that V0 is equal to V by 5. And similarly over here total volume is V. So V dash plus 3V dash is equal to V. So V dash can be written as V by 4. So let us draw FBD of each piston. So over here if we draw FBD of first case, so we have a piston here and we are making a piston over here as well, which will be demonstrating the other case. So in this case the mass of piston is in the downward direction, mass of piston multiplied by G. The pressure on this side is exerting a force in the upward direction which is equal to P1 into area A, and pressure on this side is exerting force in the downward direction P2 into area A. So if we write an expression for this side, so we can say that the mass of piston times G, the force in the downward direction, must be balanced by the force in the upward direction. So MPG plus P2A, these are the forces in the downward direction, which must be balanced by the force in the upward direction. And hence over here we write mass of piston into G is equal to P1 minus P2 multiplied by area A. So this becomes the first equation that we have. Now similarly on this side we can again say that the mass of piston is in the downward direction MPG, and over here the pressure which is acting is P1 dash times area A, and on the other side we have P2 dash into area A, and we will get perhaps the same expression. We will get MPG is equal to P1 dash minus P2 dash multiplied by area A, and this will serve as the second equation. So what is going to change is P1 dash and P2 dash. So P1 dash and P2 dash is something that is going to change, and over here if we equate the two cases, because the mass of piston on the either side is same, so we can write over here P1 minus P2 is equal to P1 dash minus P2 dash. Now to write the expression for pressure, we will be using the equation P equals nRT by V. Now again, one thing is simplified in this problem, that the moles on either side is given to us as 1 mole. So we will not be writing n, and hence over here in the first part which we have, we will be writing it as R, temperature T naught, and then volume V1. So V1 volume which we have is equal to V naught. So V naught is equal to V by 5. So RT by V by 5 minus RT upon, and the volume which we have on the upper side is 4V, that is 4V by 5. So 4V by 5, and this is equal to P1 dash. So P1 dash again 1 RT final by volume V1 dash. So V1 dash is V by 4, and then we have minus of RT final upon 3V by 4. So this is the equation that we have, and from here we can again remove R by V. So R by V, if we remove, we get 5 T naught minus 5 T naught by 4 equal to 4 TF minus 4 TF by 3. And we are solving for the final temperature. So over here we get 5 into 4, 20, 20 minus 5 is 15 T naught by 4 is equal to 12 minus 4, that is 8 T final by 3. And hence from here we get the final temperature as 15 into 3 by 8 into 4 T naught. So 15 into 3 is 45, 8 into 3 is 32, 45 by 32 times of T naught, and T naught being equal to 300 Kelvin that we have. So this is the final temperature that we will attain, and on solving we attain a value that is equal to 421 Kelvin. So this is the final answer for this particular problem, problem number 2.6.